All right, everybody. Thank you. I'm your last talk, so hopefully your brain is filled with all sorts of good and exciting information. And I'm going to close us out at the end of also this really fun celebratory week of both two laureates that are seminal in the field, but also just the field itself, where the field is at right now, and how we're doing in the field. My talk's going to be a slightly different variation, and I have to start with something that's a little bit of a soapbox of mine, and that is that the Kavli Prize this year was given in exoplanet studies, fantastic, but the word planet is problematic. Can everybody just agree? I feel like I should have gotten more of a reaction out of that. The word planet, do you want evidence for this? Walk into a division of planetary science meeting and shout out, Pluto is a dwarf planet, and see what happens. Punches will be thrown. Also, small children across the world are very upset that planet has been demoted, in some ways, according to some, to dwarf planet, and we get letters about this all the time at the American Museum of Natural History because we don't have it on our planet display. Okay? That is the low mass end of the problem with the word planet, or the definition. The high mass end of the word planet is equally problematic on the definition side. Being able to differentiate between the end of the star formation process and the end of the planet formation process and, did I say that wrong? The start of the planet formation process at the highest mass end and the end of the star formation process at the low mass end, they overlap, and it's real hard to differentiate between the two kinds of objects. So as you heard, the name of my research group is Brown Dwarfs in New York City. So I'm going to be talking to you about a class of objects that are called brown dwarfs. But as the title of my talk demonstrates, I'm not calling them brown dwarfs, really. I'm going to call them cold worlds, and hope that your brains can get as excited about an object that doesn't have a host star, for the most part. One of them does, but barely. It's very widely separated from it. No host stars involved, okay? Yes? Back of the room, we're going to be good? Yes. Okay. A little bit on exoplanet history as well that I have to go into here that demonstrates how these two fields that are really the same field have interacted with each other. So you heard about this paper earlier. I think most people in the room would know this paper, the Nature paper from November 1st, 1995, entitled Jupiter Mass Companion to a Solar-Type Star, really shepherded in the field that we're all here doing as observational theoretical exoplanet scientists. Michel Mayor and Didier Queloz won the Nobel Prize for this in 2019. But did you know, if you read the abstract for this, they had to be speculative of the kind of object that they had discovered at the time. There was a hunt for exoplanets on, and there was a hunt for brown dwarfs that was also on at that exact same time. So if you actually zoom in on that abstract, whether you realize it or not, they weren't sure what they had found, and they had to be speculative. And in the speculative side of it, you can see that the object they found might have been a gas giant planet that's migrated to this location through orbital evolution, or it could have been this other kind of object that people hadn't found yet. Could have been from the radiative stripping of a brown dwarf. We had yet to find the brown dwarfs on November 1st, 1995. 29 days later, in that exact same journal of Nature, came this paper, The Discovery of a Cool Brown Dwarf. Now, no Nobel Prize has been given to this, but it's really great shepherding in of a field, and this shepherded in atmospheric studies of brown dwarfs. Cold atmospheric studies began with the discovery and characterization of Gliese 229b. All right, so what are the brown dwarfs? The things that I love so much out there in the solar neighborhood. Well, this is going to be my little schematic to explain them to you. So Jupiter is on one side of this, and there's no debate that Jupiter is a planet. Okay, I wasn't trying to get anybody to throw a punch on that. Jupiter, planet, good. The sun, on the other end of here, is your other mass range that I'm going to give you. Now, We think that stars form through the collapse of a giant molecular cloud that fragments into pieces. You get big pieces that make big stars, and you get smaller pieces that make small stars. But in the 1950s, it was theorized that actually you could fragment a piece off that was so small that you could not get nuclear burning in the core of the object. Nuclear fusion would not occur. And that would happen at around 75 times the mass of Jupiter. That's metallicity dependent. It really depends on the material that you collapsed from. But right about there was the theory that there could be these objects that didn't have nuclear burning. But the smallest fragment wasn't necessarily the thing. It was just like, let's find these objects that don't have nuclear burning on them. Planets, of course, brown dwarfs actually have they don't have nuclear burning, but they can have heavy hydrogen burning. You can actually get a little bit of heavy hydrogen burning early in the lives of the brown dwarfs. So that really is one way to define them as objects with no nuclear burning. But you can get all the way down to 13 Jupiter masses or so, and then you get below the nuclear burning boundary, but you can still fragment those kinds of pieces off via the star formation process, which is why you can have overlapping objects that are a couple of Jupiter masses that formed in a disk around a star, which is how we think that the Jupiter-like planets here have formed, or they could have formed through the fragmentation of a giant molecular cloud. So they overlap. Now, at this point in time, there are thousands of brown dwarfs that have been discovered, many thousands of them. I'm going to really focus on the ones that we have spectra for, because this is going to be an atmospheres talk where I'm going to show you a library of the coldest brown dwarfs that we know of, and what their spectra look like. They really are going to be very analogous to Jupiter. But the brown dwarfs come in different flavors. There's the M types. Dave talked about this in his talk, but was only talking about the stars part. But what was hidden in there is actually, there's some brown dwarfs that are actually M types, M class objects. They're very hot, they're just young, and they haven't cooled out of that phase yet. Then there's L types. You can also get some stars in the L types. Many people don't remember that the L types also have a stellar component to them. And then there's the T's and the Y's. I could give you a whole other amazing talk on the kinds of overlap that we get in exoplanets and the L types, but I'm not going to do that today. I'm going to focus on the coldest ones, because if you look at the temperatures that I've written down for you at the bottom of each class, you might notice that these Y-type objects, the Y class of objects, go all the way down to 250 degrees Kelvin. Jupiter is about 125, 150 degrees Kelvin surface temperature. So we are truly able to bring you a library of objects. When I show you the Y dwarfs, which is what I'm going to do today, I'm going to show you what we've been doing with the James Webb Space Telescope and getting spectra of these objects that really push us all the way down to Jupiter-esque temperatures. Call them a planet, call them a brown dwarf, doesn't matter. All right. Now, you may naively say, I'm going to show you the library. I promise, you're going to see real data shortly. But when I do, you may naively think there's a way to organize all of the objects. And maybe if we could just figure out what the mass and the temperature were for them, if we could just figure it out, we could organize them in a way that was logical and nice. That's not going to happen today, just so you know, because it's not just temperature that is organizing these objects. Instead, there's all this other stuff, some of which is observational, some of which is just intrinsic in the object, and some of which just overlaps. So the metallicity might be different between the objects, gravity might be different, age might be different, non-equilibrium chemistry. Diana brought it up, and I'll just keep bringing it up. Non-equilibrium chemistry is the new pain in the butt in atmospheric investigations. Binarity, you might be looking at two objects and you didn't even realize it. That's going to happen to you observationally. Viewing angle, are you looking at it pole on? Are you looking at it equator on? That will change everything about what you see and characterize in the object. Clouds, 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 clouds. Problems. Love them, but they are very hard to decipher and figure out in objects. Aurora, you'll see some of that. Vertical mixing, all of these parameters together, you have to figure out all of it and all of it at once if you're going to figure out your library. Now, what I'm going to show you is JWST data. And while the JWST images go viral on Instagram and TikTok and Snapchat or whatever the kids do, we don't have images of objects. Instead, we have spectra. I'm going to show you a spectral library. So recalibrate if you were hoping to see. I don't think I have to say this to this audience, but sometimes I have to say it. I'm not going to show you images. I'm going to show you a library of spectra. And when I do, I'm going to show you what elements and what molecules are shaping that spectra. So let's have a quick look at the periodic table. And I'm going to tell you what elements here we have detected, solidly, directly detected, in the atmospheres of brown dwarfs over the years. Now, this runs the gamut from the hot ones to the cold ones. They got a lot of hydrogen, and so you get a lot of hydrides. You get a lot of oxides, so you get chromium hydride and calcium hydride. You get titanium oxide, vanadium oxide, iron hydrides, lots of this stuff. But I'm going to focus on the cold objects, so there's only a couple of elements that you're going to have to remember, and that's going to be hydrogen, carbon, nitrogen, oxygen, phosphorus, and sulfur. Those are the ones that I'm going to tell you a lot about today, because they form the following molecules: water, carbon dioxide, carbon monoxide, phosphine, methane, ammonia, and hydrogen sulfide. A combination of these molecules will shape everything that you're going to see for the rest of the talk. To give you a hint at what we've been seeing, I'm going to show you a model of what was predicted pre-JWST for what you might get for a cold world atmosphere. And that is going to be the only model I show you for the rest of this talk. Everything else is going to be data. So here's what the model prediction for a 450 degree Kelvin object looked like. I could have shown you anything in a suite of models. There's a lot of different models that are out there. I just chose one that I actually uploaded to the JWST exposure time calculator when I was planning a bunch of programs, and that was the ATMO 2020. I chose a chemical equilibrium model, log G of 5, 450 degree Kelvin object. The important thing here is to know that when you're doing JWST observing, you're observing in the infrared. And notice on the x-axis here is the wavelength, and the y-axis I have flux. The wavelength that you're seeing here is taking you from your eye sees in the optical way, way, way over here. Everything else is a wavelength that you can't see. But most importantly, you can see that the peak of the flux of the object is going to be in here. This is a sweet spot for the James Webb Space Telescope for cold worlds. It happens around 4 microns, 4.5 microns, and that is a sweet spot for an instrument on James Webb called near spec. So I'm going to switch now from model to data. Are you ready? I heard one yes. The back of the room. Are you ready to start seeing real data? Do you think it's going to look like this? Do you think it's going to look better than this? Just say yes. Okay, we're all on board. All right. This is a JWST spectrum from the guaranteed time observation from cycle 1. It was chosen because people wanted to see what the atmosphere looked like. And here it is. Every bump, every wiggle that you see is real. This is real data. It's so high resolution that you can't even resolve out all of the chemistry that's happening in here, but I'm going to focus on that. And I'm going to point out what each one of these molecules is doing in here. This is largely dominated by ammonia chemistry, and something that I just want to say right now is that I am going to focus. This is a gorgeous spectrum because it's showing you both what the near-infrared capability is, near spec on JWST, and MIRI, the longer wavelength portion of JWST. But I'm just going to focus on this area for all of the other objects because we're at the end of cycle 3. And at the beginning, we weren't sure JWST would give us enough time to go all in on a big library of both near spec and MIRI. But at this point, I should impress you with all the data we got, and we're hoping that they let us come back and get the longer wavelength for everything else. But the library that I have is going to be focused on this area of the spectrum because it's the peak of this spectral energy distribution. So let me zoom in on it and then show you what each molecule is doing. So this is a zoom in a near spec. It's G395H. It's the high resolution version of near spec, an instrument on JWST. And this is all real data. Every wiggle is a molecular absorption feature. I have the uncertainties on there for you. They're in gray. So you can see the uncertainty in this object. I also overplotted in here for your eye cross sections for each of these molecules. Now, I do not, I'm going to take you through a visual tour, just a visual tour. But a component of our research has been modeling all of the data. And I'm not going to go as hard on the modeling. I'm going to give you a conclusion slide at the end on how our modeling has gone. But I want to guide you visually through what we've been seeing because the chemistry is so good that you can just see it across a whole sequence of objects. But I'm going to point out to you important molecular absorption. So the first one that you can see here is there's this is absorption here. That's ammonia. This big, beautiful band here is all methane, lots of methane, and the whole shape, everything you see, methane, 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 methane. Nice big, this big bump in here even has a name. It's called the Q branch of methane. This is another absorption from methane. Then this is what I want you to be paying attention to, which is why I'm highlighting it. This is going to be where carbon monoxide comes in. The shape here is carbon monoxide. The shape here and all the wiggles is carbon dioxide. And then in here is water. Now, you can also see that in different portions of the spectrum, different molecules are actually fighting each other for the absorption. So like this is water, but there's also a lot of ammonia in here. But these lines here, if I can keep the straight there, this is water lines that are in there. All right. I didn't highlight every molecule in here because while we really did think we were going to be able to see all of these molecules in these objects because they were predicted by models, we actually didn't find phosphine, which is its own annoyance here. Because it's in gas giants, so you actually see it in Jupiter, and we scaled up from Jupiter and thought for sure at the warmer objects we would find phosphine, and we did not, except for one object, and I'll show you that one at the end. And then hydrogen sulfide is also an opacity source, and like I said, I'm going to show you a visual tour, but we've modeled all of these objects, and I can tell you that the models require the hydrogen sulfide in order to correctly model the data. We've both done forward modeling, and we've done atmospheric retrievals on these objects, but there's no good feature for me to point out to you, so I'm not going to ask you to look for it. I'm going to ask you to look for all of these other molecules. And how I'm going to do this, I'm going to show you the Cold World Spectral Library. There are 14 objects that I'm going to show you here. They're all the same wavelength. I have highlighted what to look for, which molecule to look for, and I made a video. And I'm just going to run the video. And the video is going to show you as changing temperatures from a warm object, this one is at 809 degrees Kelvin, all the way down to the coldest object, which is going to come in at around 280 degrees Kelvin. And I want you to look at what each molecule is doing to the spectrum. Now, when we created this library, our thought was that maybe we would have a nice, maybe even like vaguely nice, organized spectral sequence where you could see very clearly, say, what the carbon monoxide did or the carbon dioxide did. Because you make a prediction that with a changing temperature, you should see an increase or a decrease of any given molecule, depending on what chemistry tells you that a given molecule should do at a given temperature. But as you'll proceed, when I hit go, you're going to see this is a bit of a mess, maybe as expected by some. All right, starting at 809 degrees Kelvin, pick your molecule that you want to watch, and I'll play it a couple of times so you can watch what each molecule does. So that's 809. And now you're seeing the change in each. These are different objects, 14 different objects. They are not related to each other. These are just a temperature sequence of objects. This is taking you from a warm object to a very cold object that's basically in the Jupiter regime temperature. So maybe, to start, have a look at that methane. Once we get to the warmest object, the signal noise, by the way, is about 5 to 20 in this band and about 30 to 70 in this band. And so out here we have our lowest signal, and actually in the methane band we have the very lowest signal because the absorption is so strong. So maybe pay attention to this methane band. There's something in there you might be able to catch that happens in the methane as you go down in temperature that struck us right away. Then maybe pay attention to the carbon monoxide. What the heck's going on there? That's what I keep asking myself. Look to see if you see patterns. You're seeing the shape come, you're seeing the shape go, you're seeing the shape come, you're seeing it strengthen, really strengthen on that one. And then maybe glance up and look at the temperature and see if it's making sense to you. Here's carbon dioxide. Watch that one come and go. This is normalized flux because I wanted you to see the shape that each one of these molecules takes on. You can see the water lines, see the depth of those water lines as they go down, and then maybe compare them to, so this is a low signal to noise portion of the spectrum in the ammonia, but at least the ammonia measurements do seem to play a little bit nice, as opposed to the carbon monoxide and the carbon dioxide that seem to go all over the place with temperature, both increasing and decreasing. So I'm going to break it down for you in the next slide. Let's have a look at the sequence. This is all of the objects on top of each other so that you can see them all in one go. And you're seeing the methane here, so the ammonia here. You can really see the ammonia here. Can you see it? Can you see it? I want you to see it. Do you see that? That's the line. There it is. I look at it so much. I want you to be able to see it too. It's there. It's there. It's there. Methane should be very obvious to you. It's big, it's broad, and then look at that. Look at that beautiful 3.326 micron Q branch absorption of methane, plus all of this methane in here. More methane, CO, CO2, and water. Let's zoom in and talk about what might be going on with specific objects in here. This is the warmer portion of the cold world spectral library, and I want you to look at the methane again. Did anybody see anything weird? Nod. I see 1 nod, 2 nods, 3 nods, 4 nods, 5 nods, 6 nods. All right, let's highlight it. So yes, that Q branch is great. That Q branch absorption, 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 and then boom, something happened. Something happened that we did not expect to have happen, which was we didn't see the methane in absorption. We see it in emission. And emission in an object that's 450 degrees Kelvin, or thereabouts, was very, very unexpected, because that's not an easy thing to have happen in an atmosphere of a cold world. There's just not enough heat, there's not enough energy in order to get that to happen. So instead, we modeled it, and we realized what we needed was, we needed extra heat in the upper atmosphere. We turned to the solar system for help on this, as this is an issue that happens in the solar system. In the outer solar system planets, Jupiter, Saturn, Uranus, Neptune, they have extra energy in the upper atmosphere. And for them, it is, it's related to auroral processes. It's related to energy they get from the solar wind that can cause an aurora on them. It's not the full reason. They get energy from the sun, but then they get an auroral process. In the case of Jupiter, I'll tell you as an example, it does get this extra energy from the sun, but there was even more than they could expect. They called it the energy crisis of the outer solar system. And one of the solutions for it came by noting that there's extra heat that can come from an aurora contribution, in the case of Jupiter, from Io, its satellite moon. It's a highly eruptive, active moon, and it sends a plasma towards Jupiter that creates auroral spots. In our case, we're going to get extra energy. Auroral processes feel like a really good way to have that happen. We were able to model it. We know a thermal inversion would be necessary to get that. We don't have a star, though, to help out. So possibly this object here, 1935, has its own companion that's helping out to give it that methane emission. But because otherwise, its spectrum isn't showing you anything else that's strange. This methane emission is happening high up in the atmosphere of the object. So that's one of our odd objects in here. I'll point out another one to you. This object here, 0146, I had put on our target list because it's a known binary. There are 2 objects there, not just one. So you're getting 2 for the price of 1 in this spectrum. So a lot of methane in here, kind of looks normal, but I'll highlight the CO and the CO2, I think look a little bit strange, and we've been attempting to model this object. A former postdoc in my research group, new professor at Amherst College, Daniela Bartolez-Gaglufi, is leading this paper, which we are just about to submit, that shows how this is the first cold world combined spectral light binary. This is what happens when you have 2 cold worlds that have a combined light, and you're getting the spectrum for them, and you have to differentiate what you're actually seeing. And I think the CO and the CO2 are a telltale sign of what's happening in this object that has a combined light, because the CO and the CO2 really don't play nice in the sequence anyway, and you're combining 2 objects that have disequilibrium chemistry in their carbon. Using that object as a template, we thought maybe we could find other spectral binaries, other objects in this sample that we didn't realize were binaries, but maybe they are. And just looking down to the next one, this object called 0535 struck us as also unusual, and we think this one may very well be a spectral binary as well, where you have 2 cold compact objects that are together. Moving on to another object here I can dissect for you. This object here, 0751-76, is sometimes referred to as an object called Coconuts 2b. It is in the exoplanet library. It's considered an exoplanet. It's one of these objects that, I don't know, could start a fight if you said Coconuts 2 is a planet versus Coconuts 2 is a brown dwarf. I really don't care what you call it. But this object is orbiting very widely a very low mass, very young M-dwarf. Very young, meaning 100 to 300 million year old M-dwarf. And 2 people in my group are writing up this result. Jess Copeland, who's a grad student at University of Hertfordshire, and Rocio Kimmin, who's a postdoc at Caltech. Given that this object is so important to both the exoplanet community as well as the brown dwarf community, we're giving it a lot of attention. And one thing I'll just point out to you here is note again the carbon sequence. This has very strong CO2 and CO absorption in it, indicating that gravity also likely seriously impacts the carbon chemistry in a given object. All right. On to the colder portion of the cold world spectral library. I'll zoom in now on the bottom because I'm giving you the sequence again. Love it, appreciate it. All of this is real data. All of these objects are directly observed. Warm objects down, maybe binary, low gravity auroral object. We're trying to dissect what each of these things end up doing to an atmosphere. Let's zoom in on the cold ones. And in this case, there's an object in here in this sequence that really bugged me, really bugged me. And that's this object here. So this object, WISE-0503, which, just as a shout out, was actually discovered by a citizen scientist named Dan Castledon, who worked with me on this project called Backyard Worlds. So this is actually the discovery of a volunteer. He found it, and we've been following it up. And we followed it up with James Webb Space Telescope, and we got this spectrum. It's got very strong methane. It's a very cold object. It's the second coldest object in the sample, 375 degrees Kelvin or so. But it's got major CO2 and CO absorption, really out of sequence. We've modeled it, and it looks like this object has a slightly higher metallicity, not like super metal rich, but metal rich enough. And this is a paper that's going to be written up by another grad student I'm working with, Melanie Rowland, who's at the University of Texas at Austin. But most notably, this object is really nailing down that the carbon chemistry is not in equilibrium. It's a very disequilibrium state. Moving on to the coldest object, at the bottom of the sequence is perhaps one of the most famous and underappreciated brown dwarfs that exists, cold worlds that exists. It's called WISE 0855. This object is the fourth closest system to the sun. If we have to jump ship and go somewhere else, 0855 is going to be one of your choices, okay? Keep that in mind when you start thinking about brown dwarfs. 0855 has major methane absorption in here. It's 280 degrees Kelvin or so. The reason why it looks a little bit different is because this data didn't come from my program. It came from a GTO program and was published by Kevin Luhman in 2023. But we have reanalyzed the data and modeled it, and it's a slightly lower resolution. So this is G395M, or medium resolution data, which is why it looks like it's a slightly poorer quality than the rest of the data. Melanie Rowland also performed the atmosphere retrieval on this object, and you can see that the CO and the CO2 are very different than the other objects as well in the cold sequence. But the thing that's important that I want to point out to you about this object is for this one, we were actually able to retrieve phosphine. It's the only object for which we could constrain phosphine in the atmosphere of the object, and we were also able to constrain via modeling that it has deuterated methane in the object. Deuterated methane and phosphine in the coldest object. Very exciting object. All right, back to your sequence here. So this is one way to look at all of the objects. We need to dissect them and put them in a sequence with each other. I did not go into all the modeling that we did on these objects, but I do want to give you just a quick summary of what all of the models ended up looking like, or what the models were telling us. So insights from cold world spectra, love it because I'm going to change the slide. I just want you to like it. Do you like it? Yes? It's a very, very strong sample. All right. From the modeling, the cold world library, one of the things we did is we measured out and we got the abundances for all of the molecules that I have mentioned. And we investigated the carbon to oxygen ratio, as that can be one of the tells on maybe how the formation pathway of the object. But both the carbon to oxygen ratio as well as the isotope logs of 12CO and 13CO come in at solar levels. So this sample that runs from 800 degrees Kelvin down to 280 degrees Kelvin with objects that run the gamut from 6 Jupiter masses to 35 Jupiter masses all come in at likely formed via the star formation process. And then the other thing that's key is that in order to model these objects properly, the models asked for clouds. I can't tell you exactly what cloud is going to be the right one for these objects, but we're testing the water ice clouds, we've tested sulfide salt clouds, and it's clear from the modeling exercises that we've done that a cloud is a better fit, but we are still working on exactly what that cloud is. And then through the modeling, the phosphine and deuterated methane were detected. So the conclusion you get from just looking at the spectra, though, is the peak of the spectral energy distribution for cold worlds, it does not follow a clear temperature sequence at all. Auroral processes are present, which really, so good. And cold world atmospheres show this strong presence of disequilibrium chemistry and probably non-uniform vertical mixing throughout. So I'm going to end with this note that the insights that I draw from cold worlds is it's a zoo out there. We need these libraries. We need them. We need observed libraries coming directly from worlds beyond our own in order to pick apart what is out there, because you need to expect diversity, but there's also out there so many surprises. So diversity and surprises are on the horizon as we get more and more and more atmosphere insights in the coming years with both JWST and ELT and any other large telescope that somebody wants to build. I'll stop there and take any questions.
So, questions? Yeah. Ignace?
Thank you for a very nice talk. The CH3D, is there any hope that you can measure that for some of the other objects, or is it really because it is so cold you can actually do this?
Oh, we tried. And well, I'll tell you. So it's the only one that's constrained. It's just constrained in this one, but this object, WISE 1541, showed a hint of it, which surprised us because it's warmer. And it's so subtle, the feature, that the paper that Melanie has written is also our attempt to tell the community what it is that you need, what resolution you need, what temperature you need, and what mass you likely need. Because if it's a mass thing, which it also should be, then this object, which I called low gravity, 0751, should have had it. And we even injected deuterated methane abundances in Jovian levels to try and back it back out and see if we could get it. And we would have been able to detect it if it were there in 0751. So it's still a little unclear to us when you're going to get it, how you're going to see it, but we are trying to help the community because a lot of JWST proposals want to write saying they will detect the deuterated methane in their directly imaged world as well. I know you know. But we've got it. We've nailed it. It's there. It's in 0855. In 2 different data sets, too. Not just 1, 2. Because we have a separate data set in 0855.
Hi. Are there other cold brown dwarfs, like the coldest one on the list, that you could observe, or does it lie alone in its category?
Ooh, thank you, Sarah, because this is my JWST Cycle 4 proposal. I need the TAC to get on board. There's nothing that quite rivals 0855. It's a very strange object, but we have candidates, if the TAC would just give us time, that compete with 0855. So maybe they're 290 or 300. Nothing we have looks like it'll come. Yeah, I would tell you 10. That is my JWST Cycle 4 proposal as well. So you want to see it, get on that TAC and say yes.
I'm sure that if anybody here is on the TAC, they've heard it.
Well, I don't know.
So they don't all have the same gravity. Do you see consistent trends with mixing across what you expect their gravities to be?
No, we don't, and it's annoying. From the forward modeling, what we've figured out is that, so we've done forward modeling and we've done retrievals. The forward modeling, I should say, is being led by Brianna Lacey, who's amazing young researcher. She's at UC Santa Cruz right now. And one of the things, and I should also say that Brittany Miles, who's a close collaborator of mine, has a couple more objects that I haven't put on there. And what we found is that for the warmer objects especially, you need 2 different vertical mixing in the forward models. If you combine 2 different vertical mixing KZZs, you can actually kind of combine to Frankenstein out the CO and the CO2. But it's not the same combination of KZZs for any 2 or 3 objects. It's different across the whole sample.
Is your resolution good enough to measure rotation rates on these?
Ooh, I have an object I want to show you guys so badly, but because it's brand new. It's like literally, we got it last week. And I didn't show it to you because this is recorded, right? Because that's what scares me.
It's not streamed, but it's recorded, yeah.
It's getting put somewhere. All right. Anybody that wants to see it, I'll show you later because it's totally bizarro, this new object that fits in the sample. In this object, it's very old, and so it is spinning very fast. And so in that object, we are able to get the V sin I out because you can see how broadened the lines are of the methane. So for some of the objects that are rotating fast enough, we are able to get a V sin I in those. But a lot of them aren't spinning fast enough for us to, or the resolution is good enough if it's rotating fast enough, is the answer I have for you. And one object, at least one, is rotating fast enough that I'm pretty sure we nailed it. We have the V sin I.
Yeah, great talk. Do you expect variability in those spectra?
Oh, definitely. We definitely have variability. Also, Cycle 4 JWST proposal from our team. Yes, so these are the warmer ones, and you might be familiar with our work on, the colder ones, and you might be familiar with our work on the warmer ones. We've had two really good, one of them's not out yet, but it's about to be out, it's submitted. We did a spectral monitoring of WISE 1049A and B, the third closest system to the sun, and that's a warmer set of objects. That's up more at like 1200 degrees Kelvin. These objects are colder, and there's unpublished Spitzer data on several of these objects that demonstrate that they have a rotation period. And so there's an expectation that we should see these objects show variability. So we would like to put in a spectral variability monitoring program for the coldest ones. Most notably, I really want to go after the Aurora object, WISE 1935-15, because that one should certainly show variability for a lot of reasons.